Thank you very much, all of you, for coming. We have three speakers today, and two of the talks are going to be in English. So let me introduce the first speaker, Martin. He works in Italia. He's an outstanding engineer. He's been working with WebRender, which is right. It's one of the parts of Servo, of the browser engine. And well, I think he's going to talk about it better than me. So Martin, please.
So what we've been doing in the Gecko and Servo community around WebRender. I work for a Galician consultancy called Igalia. We've been doing this sort of stuff for a lot of years: browser development, compilers development, software-defined networking, that sort of stuff. So a little bit about me. I've been working on Servo since about 2014, and WebRender specifically since 2016, working in Rust, which is a really great language and a really great escape from C++. So I find it's really great, and it's exactly what they say. It's programming without fear. So I'm really happy about that. And yeah, so I'll get started. So WebRender is a web page rasterizer, which no, I just forgot to switch the slide. So page rendering is the last stage in the process of producing a web page. You start with all your scripts, in your JavaScript, and your HTML, and your CSS. And at the end, you have the video output, which is the rendered output, and maybe audio as well. Page rendering is really, really performance sensitive. So if you do the math, you have millions of pixels that you need to update 60 frames a second, or else it's not going to look very well if you miss a frame. And the other thing about page rendering is that it's really deeply integrated into input handling, which means that if you imagine a cell phone or a mobile device and you're using your finger to scroll the page, the time between when your finger moves on the screen and when the page needs to update that period of time is really sensitive, because our perception falls under about 60 frames per second. So if you miss that frame, it starts to look really bad, and we're really good at seeing when those don't match up, which means that page rendering is on that critical path to a really good experience. The other thing is that page rendering traditionally is one thing that takes a lot of CPU time from the other CPU-intensive parts of web page rendering, such as script and layout. And anything we can do to reduce that allocation of the CPU time means that there's more time for those other really expensive tasks, which are also very important to getting a good web page experience. And finally, usually when a web page is messing up graphically, the renderer has something to do with that messing up. Scrolling jank, which is what happens when you're scrolling, and it's scrolling smoothly, but it stops, and it starts scrolling again. That's called jank. Or animations that are choppy. That's also usually the fault of the renderer. Or rendering bugs, which are thankfully not that common, but they do happen. Especially as the GPU is used more and more, you start seeing more GPU-specific bugs. For instance, maybe you see the border of a div element that doesn't look quite right. Those are typically problems with the rendering engine. Oh, I also want to say I'm speaking English, so if anyone can understand me, just raise your hand and ask me to repeat myself, and I'll do that. So I want to talk a little bit about history. So this is ancient history. I remember these days, and less fewer people do, which is, I think, a good thing. But this is the sort of historical version of a browser rendering engine, and this is still a good model to conceptualize it because really everything that we have nowadays is built on this model, and all the decisions that we've made since then are a result of this model. So basically, what you have are you start with this collection of HTML, CSS, and JavaScript. And the HTML is turned into a DOM tree, which is the traditional DOM tree that you get from parsing something like XML, structured markup. And that's really not very different from what you get from an XML parser. But the second stage, the CSS and maybe some JavaScript interaction combines with that DOM tree to create what's known in Gecko, at least, as the frame tree. In WebKit, this is called the layout tree. It's got a lot of different names. In that process of combining the CSS and the HTML is called, in Gecko, it's called reflow, and in WebKit, that's called layout. So I might interchange those terms since I've worked a little bit on WebKit and on Gecko. So sorry about that. So essentially what happens once you have that tree is that you have all the information that you need to paint the web page. It's all just in this abstract data structure. But there is one caveat to that thing, which is that data structure contains links, usually pointers in C++, back to the DOM tree, and maybe even back to the original source, if we're talking about strings. So there's some pretty strong dependencies in that graph from the layout tree. But typically what happens in this historical model is that there is some code that walks down the frame tree recursively, and it calls directly into a 2D painting API, which is like an API like Skia or Cairo. And if you're unfamiliar with those libraries, you can think of the Canvas 2D library. It's essentially the same thing. You know, the library knows how to draw a rectangle, knows how to paint text, and that frame tree is the data structure which is walked by this code to produce some rendered output. But not surprisingly, there are some problems with this model from the year 2003, 2004. And those problems are that is that we have to touch that data structure, that frame tree, to repaint, which means that, for instance, you scroll the page, because this was before touch screens mostly, so you click your mouse wheel, and we need to immediately touch that data structure, which is a problem if it's already doing a layout, which, like I said before, layout is also like one of the more expensive processes in web page rendering. So what that means is the layout finishes, we walk that layout tree, the frame tree, and we paint again. But that layout might take up to 1 or 2 seconds today, even, if it's a particularly bad web page, which means that you're going to see that. You're going to see your page jerk, and it's going to be a really bad experience. You're going to have a bad time. You're going to write your friends and tell them how bad the web page was. Yeah. The other problem is that there's this new feature that new from 2010 or something, which is only a decade ago, called 3D transforms and WebGL, and really we like to tell ourselves these myths about how we develop new systems. So like we say, like, oh, we came up with this new design. But typically there are events that happen which are motivating to create new designs. And I think that in this case, WebGL and 3D transforms were a motivating event to get away from this model. Because, like I said before, the APIs that are used to paint the contents are 2D APIs. They don't know how to draw 3D elements. They don't know how to do perspective transforms. So essentially, the web engines needed a new model. And that new model looks in just about every browser engine a bit like this, uh, where you have the DOM tree, the frame tree, but now instead of instead of having this frame tree and reading it, you produce this display list. And this part, I want to say this part does differ a bit between browser engines. Some engines don't always produce a display list. But the display list is basically just a high-level representation of what's on the web page. And I'll talk a little bit more about display lists later, but essentially think of it as like square here, text here. The important thing is it doesn't have anything to do with the DOM tree or the frame tree. It's erased all those links. And then that display list in the web engine is converted into a layer tree. And I'm talking about a lot of different things, but you can just think of layers as I have a web page and I want to divide it up into separate pictures, which are more or less independent, and those pictures overlap on top of each other. Maybe some of those pictures are transparent, they have opacity. Maybe some of those pictures are transformed. If you are familiar at all with GPUs, you may see where this is starting to go. Because what you can do with those layers is you allocate a texture for them on the GPU, and you call your 2D rendering API, and you tell it to rasterize just the piece of the layer tree or the frame tree that's inside that layer into the texture. Or you rasterize onto a 2D image and then upload it to a texture. It depends on the web browser or your GPU, a lot of things like that. And those layers are placed into a layer tree, which has basically, this is the picture that the layer represents, this is where it's positioned in 3D space now.
Martin, excuse me, we had a very little technical problem and our screen share is broken, so I need to relaunch it.
Oh, okay.
And you can continue. Sorry.
Okay, cool, yeah.
Okay.
Yeah. Can I start over too? Because I did some things wrong. Oh, yeah. Now is probably a good time. If anybody has any questions, we can clear them up now, and then you'll understand the second part of the presentation. I'm really happy to. Oh, yeah, right here.
So what you said before about the web page like being bad, like is it possible that you could share like tips for CSS writing that could actually improve rendering? Like, is that?
Yeah. Actually, I can share a few. I'm not the best person to answer this question, but there are a few like really good general rules for making sure that the page doesn't have a really bad user experience. And like the big rule is that you want to make sure that when you're making changes to your page in JavaScript, you're not making it re-layout or reflow the entire web page. And the way you do that is you always make sure to use CSS animation APIs. That's one way. And then the other way is to avoid querying the properties of DOM elements, like their client height, client width, that sort of stuff. Querying those properties often causes a relayout. And there's probably a more up-to-date list of those sort of things to avoid. But those are the big thing, because once you start doing stuff like that, the web page rasterizer, the rendering, the compositing, can't help you, because you're always but I'm pretty sure that these things will continue being expensive. Blurs are expensive. Shadows are expensive if they have a large radius. If they have a small radius, they're much less expensive. But if you make a shadow that has like a really long radius, you're doing like a really complicated equation to calculate all those pixels. So yeah, great. I think we're back to like really heavy graphics, but that's where I start to not be able to speak with as much insight. Were there any other questions before I continue? Okay, cool. Well, there'll be a time at the end too to answer questions. So where were we? We had this tree of layers, which are basically just images, pieces of the web page, sometimes overlapping, in GPU textures. And then we hand them off to this other piece of code, which is, you can imagine it as being completely separate from the web browser engine, because, I mean, that's a good way to think of it. And sometimes it even runs on a different thread. Because remember, like, at this point, we've already stopped referring to the memory in these bits. And we hand that layer tree to the compositor, and then we basically, with some weird edge case caveats, we can forget about it. Which is great, because like we can be over here doing more layouts, doing whatever we want, and the compositor, which is responsible for producing the rendered web page, can keep rendering that page. And not only can it keep rendering that page, when you scroll, it can move the web page without requiring a new layout. So that's why when you scroll on your phone, your mobile device, it's so smooth, because it's just moving those textures around. It's not re-rasterizing the content. When it does re-rasterize the content is, maybe you remember seeing this at some point, you scroll so far that you start to see this checkerboard pattern, like a chessboard, and that's basically layers that haven't had their contents rasterized in this part yet. And it's expensive, so sometimes it takes so long that those things appear on screen and they're not filled yet. That's sort of the, well, I give up. I can't render in time, so I'm just going to move the layers around and display something. So this is what almost every web browser does today. More or less this thing. This is sort of the consensus that we have right now about how best to render a web page. And not surprisingly, there are, I think I skipped one, yeah. There are some problems with this approach. The good things are what I mentioned just now. But the problems are, oh, I should also mention that like another cool thing about this layers approach, it's not bad, it's pretty good, is that say like part of the page changes, the web engine maybe has the capability to detect that it's only in that one layer that the change happened. So it only writes into that layer and re-uploads that layer. So it can actually be quite cheap to update your page, which is great. There are some problems. So before I said that these layers actually overlap, which means that you have, I don't know, a 4K screen. It has, many, many pixels, and it's really hard to like write all of them. Now imagine writing all of them multiple times. That's what happens when layers overlap, because you have to draw the layer, and you have to draw a layer on top of that, and on top of that, and like every area that has like overlapping layers is a chance that you had to not do something redundantly that you didn't take. So we're sort of wasting the GPU time rendering these layers on top of each other. The other problem, and this is a big deal on embedded devices which have limited memory, is that each of these layers, again, overlapping means that you have multiple screens full, potentially, of GPU memory devoted to these pictures, where maybe you're not even showing them all. Like maybe, for instance, if you imagine this is a web page, this entire background is white. So I have all these textures full of white color, and I didn't need to keep those around, and maybe I'm using a lot of memory to store those things. And additionally, we're not using the GPU as much as we could. When you're running an OpenGL game, it's using the GPU to render pretty much everything. So, but see, we're still rendering all of the things that you see are, apart from WebGL and maybe some video, are rendered on the CPU. There's some really, hot code on the CPU that's iterating over pixels and measuring distances to vertex points, and it's doing all of those things on the CPU. But like all of our computers have a separate processor that's like made to do that thing, and we're not using that processor to do that. We're still missing the opportunity to use the machine to its full extent. And finally, this approach of rendering layers on top of each other, GPUs were really made for games, although they're used for everything now. So like games are typically games and CAD applications are typically like the most GPU intensive applications. Like they have a very particular way of using the GPU. And graphics APIs and GPUs in the hardware are designed to be used that way. So if you use them in a weird way, you're going to see a really huge cliff in performance, and you're going to find performance cliffs all over the place. In fact, games that use the GPU in slightly different ways find these performance cliffs. And there's always this back and forth between GPU makers and game engine developers to try to find the right balance there. And finally, this pipeline here is really deep. There's a lot of steps, and if there's a performance problem that spans multiple steps, it can be really complex to fix. It can be a really tricky thing to manage the interaction between the layer tree that may even be in another processor over here in the compositor. And it makes it a lot harder to make changes, which could lead to big performance gains. So the question is, what does the ideal web rendering API look like? And this is, I think, where the point from which WebRender was started. If you could throw everything away, it started in the Servo research group, which is very much, let's throw everything away and rethink everything from the beginning sort of group. They have that space to do that, which is awesome, I think. How would we design a rendering API? Because I'm going to be honest with you, WebRender was not the first graphics rendering engine for web browsers that tried to use the GPU. In fact, some browsers do use the GPU for rasterization, but it's still not quite good enough to be faster all the time and more efficient all the time on every device. So there's a long way to go there. And basically, the answer that WebRender came up with was that the API needs to be fast. It needs to always, whenever possible, render 60 frames a second. You know, never drop a frame because you're using the GPU badly, because you're making mistakes when you rasterize. And it needs to use the GPU as much as possible. Remember, I said to leave more CPU time for layout and also script, because layout is really heavy and it runs on the CPU. And finally, when the API does use the CPU, because it will inevitably need to use the CPU for some things, it should use the CPU efficiently, which is where Rust comes in. I mean, Rust is a really great language for using the CPU efficiently, for adding parallelism to the code safely, without worrying about memory issues, and to do it in a way that's much cheaper in time, human time, to write, which again is great. And again, like I said, I talked about overdraw a little bit, about those layers that were overlapping. We're going to eliminate that as much as possible. The ideal situation when rendering a web page is that we touch one pixel one time, every pixel one time, and then if there are multiple layers of transparency, as many times as you need to calculate that value, but no more than that. We don't want to touch pixels more than once if we don't have to. We finally limit memory usage. So we don't want to be wasting a lot of memory storing textures which are mostly empty, which, it's just not very useful to us. So the first decision that I think WebRender made is that we decided to focus on CSS. And I think that's a really big point, because all of the other 2D graphics APIs that are used in web engines have a lot of features that are really useful for vector APIs. For instance, arbitrary paths. That's something that WebRender doesn't support right now. basically what WebRender supports are the things that you can make in CSS. And it seems like a lot of things, like when you just think about it. But then if you really think about it, like the things that CSS produces, there's just a small number of them. Basically, and just looking at GitHub, for instance, there are boxes. This box, for instance. The interiors of these buttons, they're just boxes. Borders, the border of divs. Images, text, and from an HTML file. Shadows, which are another CSS primitive. Gradients, so again, the inside of these buttons are probably a gradient. And then finally, this thing that's called a stacking context. And a stacking context is a concept from the CSS specification, but really you can think of it as a way to say these elements, but with some transformation, or some blending, or some CSS filters. And that's essentially applying some filters to some content that WebRender has already rendered. I'll talk about that a little bit more later, but these are the things, more or less, that WebRender knows about. These are the things that are produced when you render an HTML file with CSS. So what this means is that it doesn't do Canvas 2D. Currently, we use other APIs for that. There are other projects that try to handle those things. It doesn't handle internally WebGL. That's handled by the GPU itself. It's just laser focused on these things, which means that it can be specialized to render them. So this is what the API looks like, or sorry, the architecture of WebRender looks like in the end, which is that you have the same frame tree and to the display list, exactly the same, with some pretty big differences. The differences are essentially that, one, it's in WebRender, so it has a lot more control about how it splits things, which is important if you want to make decisions at runtime about how to split things. And the other thing is that when WebRender creates the display list, it does it in a way where each node is a dependency, a rendering dependency of its parent node. So it's not just arbitrarily split images. It's actually like, to render this node, I need to render all these other nodes. So it knows in what order to render the tasks. And that's also important later when we talk about batching. Get myself here. Are there any questions up to this point? I'm probably like 3/4 done. I think I'm okay on time. Going over. So,
I think we have 5 minutes left.
5 minutes. Okay, I'm going to go a little faster. So I want to talk about one way that WebRender tries to eliminate overdraw, and that's called Z-culling. Z-culling is something that video games have been doing for a really long time, and it's this really great feature where the GPU hardware has a concept of points when it renders objects, and one of these things is the depth of that point. So essentially, every object is assigned a z-index in the GPU Z buffer. Opaque objects are rendered front to back, whereas translucent objects are rendered back to front. And then the GPU buffer uses that Z buffer to avoid painting pixels more than once. So this is a very typical web page where you have the background, some page text, a picture of Carmen Sandiego, and then some annoying pop-up that pops up on top of the page, which is, imagine in this case that it's completely opaque. Everything underneath that pop-up does not need to be rendered. So what the Z buffer allows, what Z-culling allows, is we paint this first, and then we send this to the GPU first, and then when we try to send the things underneath, the GPU knows, like, okay, this thing is behind this, I don't need to touch it. I don't need to touch that pixel. And basically, the GPU is more efficiently rejecting things that it knows it doesn't need to show. And that means that we only touch those pixels a minimum number of times. The other thing that WebRender can take advantage of, because of the render task tree and because it was designed this way from the beginning, is something called batching, where similar things are rendered together. So if you have a bunch of opaque boxes with a solid color, those can be sent as one long command to the GPU. Because on the GPU, to switch between rendering things, say to switch between rendering opaque boxes and transparent boxes, or opaque boxes and say text or an image, it has to change the shader program that it's running. It has to change blending modes, and those state changes, as they're called, are really expensive. They have a really high overhead. The GPU is meant really for you set up everything and you send like thousands of things to the GPU to render that way, and it's got a bunch of processors and doing them all in parallel. And essentially, batching and WebRender makes us render more like games in that way, where we're just sending all of the geometry as much as we can before switching the state of the GPU. And obviously, there's a trade-off there between batching aggressively and using the depth buffer, which I won't go too deeply into that because of time. But and finally, there's caching. Like I said before, certain things are really expensive to render. For instance, shadows and blurs. And WebRender's in a really good position because it knows that it's going to have to render frames in the future, and that there's some continuity in the display list, something that 2D APIs know nothing about. I rendered this really expensive thing. It's not going away. I'll just cache the result. Basically making what we would call a layer before, but based on not something arbitrary in the web engine, but because it knows it's expensive and it knows it's going to have to render it one more time. Some of the common things that are cached are fonts, shadows, and blurs. And that sort of wraps up more or less the design of WebRender. So if you want to try it, you can try it today. The one way is to just run Servo. Servo is always using WebRender now, since a couple of years ago. And the other way is with the Firefox Nightly. The first step is to make sure that you have the GPU enabled by setting this key in about config. And then finally, once that's done, there are 3 different ways. You can set another key in about config, you can pass an environment variable, or you can build it. If you're building Nightly, you can build it with this option. And if you'd like to help out on WebRender, you can find us on GitHub, and you can file bugs. Bugs that you find in Firefox, probably better to file them in Bugzilla. Bugs that you find in WebRender itself, if you're playing with the code, you can file them on the GitHub. There are some IRC channels. People are actually really friendly there. And then there's a list of open bugs. And I am way over time, so probably there's no time for questions and comments. But yeah.